All right, so let's start chapter 3. It's the equilibrium of a particle. Section 3.1 is 1 or 2 pages of information. Section 3.2 is a few pages, and then 3.3. Encourage you to look at titles of chapters when you're reading your book, titles of sections. So, equilibrium of a particle. Particle is represented by a dot, a point. Okay, that's what a particle is. You have a condition for equilibrium of the particle. Well, if it's not changing its current state of motion, then the sum of the forces equal to 0. And so we're going to basically say the sum of the forces in the x direction equal to 0, the sum of the forces on our particle in the y direction equal to 0, and if it's in 3D, the sum of the forces in the z direction equal to 0. Well, we're just going to basically start with coplanar force systems. What does that coplanar force system mean? Let's master 2D before we get to 3D, right? Coplanar in a plane, just 2D. So this whole section will be 3D, but then applied only to 2D problems. Okay. Now, the next section is the free body diagram. If you talk to anybody, even like a senior design class that you take, the instructor may say, I want to see a detailed free body diagram of this. Show it to me. Very common. And actually the most common complaint that faculty have, they'll complain to me because maybe I taught statics, and then the students, pass statics, they go to the next class, and they'll come down the hall and say, what are you doing in statics? The students have not mastered free body diagrams. Are they learning anything? You're passing them, but what's happening? That's the number one complaint. So this is in your solids class. It's all in your structures classes. Free body diagrams. You just need to master them. And then, so maybe you've heard that. Probably you've heard that. How many people have heard something like that? Oh, this class is all about free body diagrams. Make sure and master your free body diagrams. And then, voila, chapter 3, finally we got free body diagrams. But it's such a disappointment, this chapter is, because there's no bodies in this chapter. It's a free point diagram. The body shrunks to a point. Free particle diagram, not a body. So don't worry, next chapter when we get moments of forces, we'll get more sophisticated free body diagrams. But at this point, it's just so simple. Here's a point. And then sum of the forces x, sum of the forces in the y must equal to 0 in 2D coplanar systems, and if you move to 3D. So, but the idea, we start to do this. We start to cut and focus on something. We focus on our study, we focus our study on something that we cut or isolated and made free from other things. That's where they get the word free. It's not cheap, it's just cut away, free, cut loose. So a free point diagram, free from other components or forces or surroundings. And then basically one of the key things to watch out when you're talking about free body diagrams is people will leave off important forces. And you can't solve the problem correctly if you left something out of the problem. So there you go, let's jump into it. This is a problem like you've solved in physics. I think you would have been able to solve this problem in physics. Determine the tension developed in each wire used to support the 300 kilogram package. So right here's a package, okay? It has a mass of 300 kilograms. It's assumed that there's this thing called G, gravity, and it'd be like 9.81 meters per second squared, acting downward. They didn't really put a coordinate system in here, but X is traditional horizontal, Y is vertical. Okay, determine the tension developed in each wire. Well, how many wires are there? Well, there's a wire running from A to B. There's a wire running from B to C, B to D, and C to D. Now, this wire right here, you say, oh, well, that runs down from the package up to D. But guess what? The tension in that one is going to be the weight of the package. The weight of the package down. And so that's mg. True? So I think that's so trivial. I would just say that there's 1, 2, 3, 4 unknowns, not 5. Okay, so I'm going to be asked to solve for 5 unknowns. Maybe I have to think of some symbols. Maybe I say, okay, tension in the wire A to B. That's one of my unknowns. I want to solve for it. And then the tension in the wire B to C, the tension in the wire B to D, and the tension in the wire C to D. You could have different notation, but I think that's pretty clear what we're looking for. We're looking for those 4 things. Okay, how am I going to solve for these 4 things? Well, we're going to isolate and focus our study on something. And they're going to be particles at this point. Later on, there'll be bodies that have more dimensions. So what we do is we come in and we cut around this ring at D. And when you cut it, you isolate it, and you come over here, and there's a little ring at D. I'm just going to call it D. And what do we have? I had to cut through this cable pulling down. What is that weight? It's the mg pulling down, isn't it? The weight of my canister down. And then I'm going to have going up and then going up. And now I'll put my labels on this. This is the tension in C to D. And this is my tension in B to D. So yeah, this is one of them right there, and that's the other one. Two of my unknowns are in this free particle diagram for ring at D. You shrink the ring to be a point. There's no real dimension to the ring. So if hopefully that's not conceptually difficult for you to just shrink it to a point. Now we focus on that particle or point. All right, we have a coordinate system. I like to think of the X and the Y. And I have the sum of the forces in the X must be equal to 0, and the sum of the forces in the Y must be equal to 0. So you say the sum of the forces in the X must equal to 0. That gives me an equation. Okay, probably I should have moved over some angles. What is this angle right here? Isn't it the same as this 30 degrees? Isn't that 30 degrees? And what is this angle right here? 45 degrees. Okay, so now I have my 2 angles that I need. And now I can represent some of the forces in the X. So it'll be the tension in C to D times the sine, no, not the sine, cosine, isn't it? Cosine of 30 degrees. That's pulling in the positive X. If you wanted, you could put a negative on it, and then it's in the negative X direction, or you could just put it on the other side and say, look, the tension B to D is in the negative X direction, that's why I put it on the other side of the equation, equal sign, times the cosine of 45 degrees. I have one equation with 2 unknowns. I need another equation. Let's get the sum of the forces in the Y. So we have the sum of the forces in the Y equal to 0. That gives us an equation. I'm going to put what's pulling up. So we'll have tension C to D. This time it is the sine of 30 plus the tension in B to D times the sine of 45. Both of those are pulling up, so I put them on the same side of the equation. And then what's pulling down? The weight, mg. Now I have 2 equations, 2 unknowns. Can you solve 2 equations, 2 unknowns? They're linear. There's nothing tricky about this one. Yeah, you could do that, right? Who would like to volunteer just a strategy in words? Oh, I'd probably isolate, right? Maybe I'd take the first equation and get TD is equal the tension C to D is equal to blah, 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 and then substitute it into here. And then I would have just one equation with only B to D and then solve for it. I think you can do that. In the interest of time, can I just say that you can do that? Solve for two equations, two unknowns. Perfect. Now, we have now solved for the tension here. Maybe I can erase. So we're going to find the tension B to D is 269 kilograms. Now, this is slang, but it's very, very common slang. I grew up United States, Texas, all that. Some other people didn't. They think temperature in degrees C. They think length in meters and centimeters. And if you ask them, hey, looks like, you're bulking up, you're going to the gym, you're putting on a lot of muscle. What's your weight? What are they going to give me their weight in? Kilos. Yeah. Who thinks in kilos for weight? There's a number of people, always. Yeah. And so you could probably size me up, and you could probably say, I can't guess his pounds, but I could probably get a pretty good job of guessing his kilos, right? Well, guess what? That's what is ubiquitous. It's all over. And so a lot of times people will say the mass is 30 kilograms and its weight is 300 kgf if they really want to put an extra little thing on there, like saying, hey, I'm talking of kilos as a force, as a weight. Anyway, this is the tension. If you don't like it, multiply by 9.81 and call it newtons. It's about 10. Multiply by 10 and you call it newtons. Okay. And then this was the tension in C to D. So we solved for those two. How do we go and get the tension in A to B and B to C? Well, we're going to focus on the free body or particle or point diagram for ring at B. So you get really good at these. You come in and you have now the ring at B. Have a little coordinate system, X, Y. You're going to have the tension, A to B. We're going to have the tension, B to C. And we have the tension, B to D. Somebody looks at this and says, something's wrong. Because look it, you had the tension in B to D. You're showing it going down. But over here on this other, you showed it going up. Which way is it? What happens is you isolate and draw a free body diagram for ring B and you cut it. And things that are in tension are going to be pulling away from the interior. They're going to be pulling away from ring B. And so it's going to be pulling down. The tension in this cable is going to be pulling down from ring B, but for ring D, it's going to be pulling up. Just think about it a little bit. Okay, so then we have our sum of the forces in the X. Maybe I should have figured out some of these orientation angles. This is 45 degrees, and this one is 30 degrees. And so our sum of the forces in the X give us that the tension A to B times cosine of 30 is equal to tension B to C plus tension B to D times cosine 45. Did I do that okay? And then how about the sum of the forces in the Y? Tension A to B times the sine of 30 equal to tension B to D. I didn't write that very well. B to D times the sine of 45. This one's a little easier because this is already known from the previous work. And so you can solve for this one. One equation, one unknown. That's great. Then substitute in here, and then you just solve for the last unknown. And these are the answers. Now, somebody says, let's make it more complicated. Why can't we do a free body diagram of C? You can, but when you do it, you got to I like to think of making an enclosing circle around the ring at C. And anything I cut through, I have to replace or put into my free body diagram. And I just cut through the attachment to the wall. That attachment to the wall is probably pulling back and up on that ring at C. And so it's not going to be really easy. Okay? All right. Same for this ring at A. Any comments on this one? Let's press forward. So we have cables, we have pulleys, we have springs. A cable, we're not going to have any weight to the cable. We can later, there's sections of the textbook, they have the drooping heavy cable in the presence of gravity, but at this point, no, our cables are just weightless. And they're in tension only. It's pretty hard to push a cable. It's just pulling tension. Pulley. So if I have a pulley right here, maybe I have it supported, goes up to the ceiling. It can freely spin. I could spin this way or it could spin that way. It can spin around, so it's frictionless. It's got a really good bearing right here, right in the pulley, right there. And so when I put a cable across it, comes around, maybe it goes like that. It takes a little bit, but when we get more to moments of forces, and then I would be able to know exactly the radius of that there pulley, I would be able to prove to you that the tension is unchanged in the cable. It's unchanged. So the tension here is the same as the tension there. We have constant tension in our cables, even though they wrap around a frictionless pulley. Let's say it's not a frictionless pulley. Let's say it's just a big pipe, and we have the cable come around like that. Well, you can have much different tension here than tension there. You have tension 1, tension 2. Yes, but here we have a friction. It can rotate. A pulley can rotate. So think about something like, I don't know, immovable tree or something else. Then yes, the tensions would not be the same. But for this chapter, we're just going to have frictionless pulleys. Okay. And then everybody's been exposed to springs. So a spring has a stiffness, K, it's a property of the spring. And we have Hooke's law, which says that the force in the spring is the stiffness of the spring times the stretch, and if depending on how you write it, the stretch, if it's negative, would be a compression. So the spring can be in tension or compression. It works. It's a linear spring. And that stretch would be the current length of the spring minus L naught. That would be the unstretched length of the spring. If I just took the spring, laid it on the table, has no force in the spring, it would have some unstretched length. But if I start to stretch it, L is greater than L naught, that's my stretch, and now I have a tension in my spring. And likewise, if the stretch becomes negative, then it's compression. Well, with those, we can really make more complicated problems. So here's a problem. Actually, the only more complication is what do we have right here and what do we have right here? Those are frictionless pulleys, aren't they? Okay, so the ropes connect 3 crates, crate A, crate B, and crate C. The crate A has 225 pounds. Crate B has a 300-pound weight. And the system is in equilibrium as shown. So they give us this angle, 45 degrees, and the pulleys in the position they're at. From the illustration, determine the weight of the crate C. So find this weight right there. And the angle theta. So how many unknowns? We have 2 unknowns. Okay, how are we going to solve this problem? Well, we're going to study it for a long time, and we're going to make an observation about the tension in this cable going around that frictionless pulley, so that the tension in this cable, if I cut right here, what will be the tension in that cable right there? 225 pounds. That's right. You need to make that observation. Okay. So what's the tension in the cable right here? If I cut it right there, 225 pounds. So what probably I'm going to do is I'm going to come in here and I'm going to do a free body diagram of this ring. And when I cut, I'm going to have a tension in that cable going this way. And I could already know that that tension is 225 pounds. And then I'm going to have a tension going up this way. That tension is going to be equal to the weight of C. The weight of the crate C. It's not 225 pounds. It's whatever the weight of the crate is at C, because the same idea over here. The tension in this cable is the weight of the crate in C. And then down here, going down, I have another one. So let's draw, kind of isolate it, take it away from our illustration. So we have a force, we have a force, we have a force. We're doing a free body diagram of what? Of that ring. Okay. And then we might as well put in some coordinate system, and then we'll put in, this is 45 degrees, this is unknown theta. Might as well label this one. This one was 225 pounds, and the force going down here is 300 pounds. And this is our unknown C and our unknown theta. Okay, so we do the sum of the forces in the X for equilibrium. If you do the sum of the forces in the X, we have 225 pounds pulling in the negative X direction times the cosine of our unknown angle theta equal to C pulling in the positive X direction times the cosine of 45 degrees. I make sure I like the equation. I didn't forget any terms. I then go in and I count. I say, there's one of my unknowns. There's another one of my unknowns. I could be the most clever engineer and mathematician in the world. But if I have one equation with two unknowns, I better look for another equation. Okay, so my other equation, sum of the forces in the Y. So I'll have the pulling up 225 pounds times sine of 30 degrees, pulling up the tension in that other cable connected to crate C, so the weight of crate C is the tension in that cable, times the sine of 45 degrees. And then I have equal to, going down, 300 pounds. Did I make it? Oh, I messed that up, huh? Yeah, this is supposed to be my unknown theta, and this is my 45 degrees. Two equations, two unknowns. How are you going to solve this? Yeah, you're going to try to get rid of maybe C. Maybe I'll rewrite this equation in terms of C. So I'll say C is equal to 225 times the cosine of theta divided by the cosine of 45. Then I'll stick it right in there. I'll eliminate C. And then I'll have one equation, one unknown for theta, and I'll be able to solve for theta, then go back. But you need to do it, please. So what you're going to find is C comes in at 287. I strongly encourage you to check that yourself. And that angle is 25.5 degrees. Any comments? Does that look doable? All right, we got whopping 5 minutes left. Don't we? Should I try another problem? Springs. All right? All right, I'll just outline this one. Two springs are used to support a 150 kilogram crate in equilibrium as shown. So the mass is 150 kilos, but they're working in the tension. You can see you have kilonewtons for the spring stiffnesses. So I'm going to get the weight. I'm going to go ahead and move over, and it'll be the M times G. It'll be 9.81 times 150, and I'll probably put it in the kilonewtons, okay? So I could just see my units. I might get my weight in kilonewtons right away. All right, now determine the stretch in the springs A to B and A to C. Well, first of all, I'm gonna do this at a two-step. I'm gonna get the tension in the spring A to B and the tension in A to C. And then I'm gonna go back to Hooke's law, and I'm gonna say that the tension force in A to B is equal to the spring constant A to B times the unknown stretch in the spring A to B. Likewise, Hooke's law here, the tension in A to C equal to the spring stiffness A to C times the stretch A to C. So get the tensions in the springs, and then get the stretch. Determine the stretch. Okay, how do I get the tensions? Isolate at this point. And it takes us a while to figure out all the information given, but we're given a lot of lengths here, aren't we? So I would focus maybe on this triangle right here. It's got 2, 3. Hey, what is the hypotenuse of a right triangle that has a side 2 and a side 3? What's the length of the hypotenuse? How about the square root of 2 squared plus 3 squared? Yeah, it's not going to be a nice pretty number, but it's the square root of 13. Likewise, I come over here, I have a 3, 4, and then, hey, what's my hypotenuse of a 3, 4, 3, 4? Oh, well, that'll be 5. Yeah, you see those really helpful to pick off my components. So what I'm going to do is I'm going to come over here, I'm going to draw a free body diagram of the ring. I'm going to put up here the tension in A to C, and I'm going to put in here a 4, 3, 5 triangle to help me pick off those components. And then I'm going to come over here, up like that. This is the magnitude tension A to B, and this triangle will be a 2, that's a 2, 3 square root of 13. And then this one coming down is my weight. So if in the x direction, you pick off 2 over the square root of 13 times the tension A to B equal to 4 over 5 tension A to C. Is that our good equilibrium equation? Sum of the forces in the x equal to 0. And then in the y, we're going to have 3 divided by the square root of 13 times the tension A to B plus 3 over 5 tension A to C is equal to the weight. 2 equations, 2 unknowns. We've done that again and again. So here are, you'll solve for those and then come back, use the spring stiffness to calculate the stretches. The stretches are not very big, 5.9 centimeters and 2.73 centimeters. Went a little fast on that one. Hopefully you can work that out. Wednesday, I'll see you Wednesday. When do we have a test? Friday. Are we going to have a class Friday morning at 9 o'clock? Yes. How about Friday 5:30 to 6:45 exam, p.m.? Okay. Thank you very much.